All right, today we're going to dive into a statistical tool that literally makes huge surveys possible. Cluster sampling. You ever wonder how national polls get their data without, talking to every single person in the country? Well, this method is often the secret sauce, but it's not quite as simple as it sounds. So let's break down how it really works and, just as importantly, where it can all go wrong.
So here's our game plan. We'll kick things off with a classic problem every researcher runs into. Then we'll see how cluster sampling swoops in as a practical solution. We're going to get into the nitty-gritty, the specific language, and the trade-offs you have to know. We'll also clear up a really common mix-up with another sampling method. And then we'll wrap up by looking at why a simple misunderstanding here can lead to some seriously flawed conclusions.
Okay, so let's start with the big challenge. Every researcher with a big idea eventually hits this wall. How do you get good data from a massive population without spending a fortune or taking, like, a decade to do it? This is what we call the sampler's dilemma. Let's make this real. Imagine your job is to figure out the study habits of students in a high school with thousands of kids. What's your first move? Are you going to try to get a list of every single student? Or maybe stand at the front door with a clipboard? You can see how the logistics just spiral out of control fast. The first method we all learn in stats class is simple random sampling, or SRS. And in theory, it's perfect, right? You get a list of all the students, that's your sampling frame, and you just randomly pick names. But in the real world, just creating that complete, up-to-date list can be a nightmare. And even if you get it, your random sample might pick one student from a freshman bio class, another from a senior physics class way across campus, and you end up running all over the place. It's a logistical mess. And that is exactly where cluster sampling comes in as this really elegant, practical alternative. See, instead of getting hung up on individuals, we start thinking about the natural groups that already exist within that population. So here's the core idea. First, you take your whole population and you chop it up into groups. We call these clusters. In our school example, these could be the classrooms. Then, and this is the key part, instead of sampling individual students, you take a simple random sample of the clusters. So you randomly pick, say, 15 classrooms. And finally, you go to those 15 classrooms and you survey every single student inside them. It's a two-step dance. Sample the groups, then survey the people inside. Now, let's get the lingo down, because you're going to see these terms everywhere. The groups you sample first, the classrooms, we call those primary sampling units, or PSUs. Then the individuals inside those clusters, the students, they're the secondary sampling units, or SSUs. Seriously, getting this PSU versus SSU distinction locked in is the foundation for everything else that's about to come. And we can even get a little more sophisticated here. So what I just described, where you survey all the students in the classrooms you picked, that's called one-stage cluster sampling. But what if some of those classrooms are huge, like a big lecture hall? Well, you can just add another step. In two-stage cluster sampling, you first randomly pick your classrooms, the PSUs, and then you take a random sample of students, the SSUs, from within each of those classrooms. This is super common in big national surveys. All right, time to pop the hood and look at the mathematical language that makes all of this work. Now, don't let the notation scare you. It's not just a bunch of random symbols. It's the precise grammar that lets us build our estimates and, more importantly, figure out how accurate they are. Okay, first, let's define the whole population at the cluster, or PSU, level. Capital N, that's easy. It's the total number of classrooms in the whole school. M sub I is just the size of any one classroom. Now, T sub I, this is where it gets interesting. That's the total value for a single cluster. So think of it as the total number of homework hours from all the students in one classroom combined. But the real key player on this slide is S squared sub T. This thing measures how much those totals vary between the different classrooms. Are all the classroom totals around, say, 100 hours of homework? Or is one class doing 20 hours and another doing 200? The bigger that variation is, the trickier our job becomes. Now let's zoom in from the classroom level to the individual student, the SSU. That symbol, Y bar sub U, that's our ultimate prize. It's the true average homework hours per student across the entire school. That's what we want to know. Then you've got S squared sub I. This is basically the flip side of what we just saw. It measures the variance within a single classroom. Are all the students in that one room pretty similar in their study habits, or is there a huge range? This whole idea of within cluster variation is absolutely central to the trade-offs we're about to talk about. Okay, so those last two slides, those were the true values in the population that we wish we knew. Now let's talk about what we can actually calculate from the sample we collect. Lowercase n is just how many classrooms we picked.
And then T hat unba, this is our best guess, our estimate for the total homework hours in the whole school. And the logic behind it is actually pretty clever. We figure out the average total hours per classroom in our sample, and then we just scale that number up by the total number of classrooms in the school. It's a really intuitive way to estimate the grand total. And that last term, S squared sub t, is our sample's estimate of that between cluster variance we talked about. That's the number we need to figure out how much uncertainty or error is in our final result. So all of this statistical machinery brings us to the heart of the matter, to the big but. With cluster sampling, there's a major trade-off. It forces us to navigate this constant battle between what's practical to do in the real world and what's statistically perfect on paper. The pros are huge. You can't deny them. It's way cheaper and way more convenient. You only need a list of the clusters, the classrooms, not every single student, which is often much easier to get your hands on. But there's a big statistical cost. Cluster sampling is almost always less precise than a simple random sample of the exact same size. And why is that? Well, because people or things within a cluster tend to be more similar to each other. Students in the same class have the same teacher. People on the same city block share a similar neighborhood. That similarity means that each new person you interview within a cluster gives you less brand new information than interviewing a totally random person somewhere else. So if it's less precise, why on earth would we ever use it? Well, it usually comes down to three big reasons. First, like we said, just getting a list of every single individual might be flat out impossible. I mean, try listing every fish in a lake. Second, geography is a huge one. If you need to survey people across the whole country, it's so much more efficient to fly to 50 randomly picked counties than it is to visit 2,000 randomly picked people scattered all over the place. And third, a lot of populations just come pre-packaged in these natural clusters, like households, schools, or hospitals. It just makes sense to use them. This example really drives the point home. Imagine you're studying the quality of care in nursing homes. A simple random sample might tell you to visit 350 different nursing homes, each for just one interview. The travel budget would be absolutely astronomical. But a cluster sample, it might tell you to pick 20 nursing homes and interview 20 residents in each. The cost savings are enormous, and they can make a study possible when it just wouldn't have been otherwise. So here's the key takeaway. With cluster sampling, you get more information per dollar, even if you're getting a little less new information per interview. Okay, it is time to tackle one of the biggest points of confusion in basic sampling theory. People mix up cluster sampling with stratified sampling all the time. I get it, they both involve grouping the population. But as you're about to see, their goals and their methods are pretty much polar opposites. Let's just walk through this table because it makes it so clear. The goal of stratified sampling is to increase precision. The whole point of cluster sampling is to reduce cost. Their method is totally different too. With stratified, you sample from every single group. With clustering, you only sample a selection of the groups. But here's the trickiest part, the ideal group makeup. For stratified sampling to work its magic, you want your groups, your strata, to be as different from each other as possible. But within each group, you want people to be very similar or homogeneous. For cluster sampling, it's the complete reverse. Ideally, you want all your clusters to look pretty much the same as each other, with each one acting like a mini representation of the whole population. And that means within each cluster, you'd want as much diversity as possible. Of course, reality is messy, and clusters are rarely that perfect, and that's exactly where the imprecision comes from. So we've covered the what and the how, but now we really need to talk about the why. Why is it so incredibly important to get this stuff right? Because, frankly, getting it wrong has some pretty serious consequences. This quote from the source material really hits the nail on the head. This isn't some minor, nitpicky error. It's a fundamental mistake in analysis that happens all the time. Researchers get a data set with, say, 10,000 responses, and they just dump it into their software, completely ignoring the fact that those 10,000 people came from maybe only 50 schools or 100 neighborhoods. So what actually happens, statistically, when you make that mistake? Well, the standard formulas you use for things like standard error, they assume every single one of your data points is independent. But in a cluster sample, they're not. Students from the same class are more alike. Their data is correlated. When you ignore that and treat the data like a simple random sample, the math will give you a standard error that is artificially and sometimes dramatically too small. And that's the real danger here. A standard error that's too small gives you a completely false sense of precision. It leads to confidence intervals that are way too narrow and p-values that are too low. You end up shouting from the rooftops that your findings are statistically significant when, in reality, they might just be noise.
You're overstating how certain you are, and that can lead to bogus scientific conclusions and really bad policy decisions.
So I'll just leave you with this question. Now that you've seen the hidden complexities that go into sampling design, the next time you see a headline about a new poll or a big study, I hope you'll just take a second and ask yourself, how did they really get that data? Was it a simple random sample, or was there a more complex design like clustering going on behind the scenes? Because understanding the method is always the first step to truly understanding the result. This explainer was based on material from the Sampling Theory and Practice course at the University of New Mexico. Thanks so much for joining us.